Hello student, I am going to discuss about in this video three-dimensional viewing. We have discussed about two-dimensional viewing and clipping in previous videos. The 3D viewing process is inherently more complex than the 2D viewing process. Why? The 2D dimensional viewing we have In two-dimensional viewing, we have 3D window and 2D viewport, and objects in the world coordinates are clipped against the window and are then transformed into the viewport for display. The complexity added in the three-dimensional viewing is because of the added dimension and the fact that even though objects are three-dimensional, the display devices are only 2D. So there is a mapping problem because though we are seeing the objects as a 3D, because in case of 2D viewing there is only 2D objects, but here one dimension has been extended or included, but ultimately we are going to display the same 3D object in the 2D device. Mismatch between 3D objects and 2D displays is compensated by introducing projections. The projections transforms 3D objects in a 2D projection plane. But also, if you want to project the 3D objects in 3D plane or 3D platform, then also you need to use the idea of projections. So this is the main pipeline of 3D viewing. First, we need to model the coordinates as like a 2D viewing. Then we have to transform the modeling coordinates to the world coordinates. Then we'll try to view transform to the viewing coordinates. Then we'll try to use the projection transformation. But in case of 2D viewing, this projection is not there. But in case of 3D and in case of 3D objects or 3D viewing, if we need to display the objects in a 2D display, we have to use the projection scheme. Then we are going for the workstation transformation, mean where we are going to display our objects. Specifying an arbitrary 3D view. We can view the object from side, top, even from behind. Therefore, it is necessary to choose a particular view for a picture by first defining a view plan. So, a view plan is nothing but the film plan in a camera which is positioned and oriented for a particular shot of the scene. World coordinate position in the scene are transformed to viewing coordinates. Then viewing coordinates are projected into the plan. So here you can see right-handed viewing coordinate system. This is right-handed viewing coordinate system. So first viewing parameter we must consider is the viewing reference point from where you are going to view the object. This point is the center of our viewing coordinate system. It is often chosen to be close to or to the surface of some objects in a scene. Its coordinates are specified as xw, yw, zw. The next viewing parameter is a view plan normal vector, and this normal vector is the direction perpendicular to the view plan, and it is defined as dx and dy and dzm. And we know that the view plan is the film in the camera, and we focus camera towards the view reference point. This means that the camera is pointed in the direction of the view plan normal. So here you can see view reference point and the view plan normal vector. So here this is view reference point, this is a view reference point, and this is a view plan and view plan normal vector. This is the normal vector. This is the camera through which we are viewing this object. So this is the view reference point. So that is we are talking about what is view reference point and what is view normal vector. This is the normal vector, or you can say the perpendicular point, a perpendicular plane with the view reference point. The view plan normal vector is directed line segment from the view plan to the view reference point. The length of this directed line segment is referred to as view distance. So that is the viewing distance. The length of this directed line segment is referred to as viewing distance. This is another viewing parameter. It tells how far the camera is positioned from the view reference point. In other words, we can say that a view plan is positioned view distance away from the view reference point in the direction of the view plan normal. So you can see 3 points: view plan, and then view distance, and then view reference point, and the view plan normal. 4 points are associated in this simple scenario. Okay. Here you can see this is the view plan, means we can say this is the camera, this is a view reference point. Okay, or we can say that the origin value, that the origin of this three-dimensional plan. This is the view distance, and this is the plan perpendicular point to the point. Okay, with the view plan. So those are the things you need to consider about in case of 3D viewing. We have world coordinate system which we use to model our object, and we have view plan coordinates which are attached to the view plan. So we have world coordinate system which we use to model our object, and we have view plan coordinates which are attached to the view plan. It is possible to obtain the different views by rotating the camera about the view plan normal vector and keeping view reference point and direction of n vector fixed. So sometimes we can fix this n plan, but we can change the direction or the orientation of the view plan by changing the position of the camera. So here you can see we can rotate the view plan. This is a view plan, or you can say this is the camera. We can change the view plan by rotating the camera, but the distance, normal vector distance, will be same, or normal plan will be same. Viewing object by changing view plan vector n. So this is the also a different idea. So here in this first case we are changing the view plan only, orientation of the view plan, not the view. This is normal plan. But here we are changing the plan vector, or we can say normal plan with the view. So that is about viewing object by changing the view plan vector n. So transformation from world coordinate to viewing coordinate. Here you can see the conversion of object description from world coordinates to viewing coordinates is achieved by following transformation sequence. First, need to translate the VV reference point to the origin of the old coordinate system and apply rotation to the aligned XV, YV and ZV axis with world coordinates XW, YW, ZW axis respectively. The viewpoint specified a world position XP, YP, ZP can be translated to the world coordinate origin with the matrix transformation. For alignment of three axes, we require three coordinate axis rotation depending on the direction we chosen for n. In general, if n is not aligned with any world coordinate axis, we can align the viewing and the world coordinate system with the transformation sequence Rx, Ry, Rz. Three different transformation with respect to x, with respect to y, with respect to z that we have discussed about rotation, transformation rotation in case of 3D in the last video. That is, we first rotate around the world xw axis to bring zv axis. Finally, we rotate about zw axis to align yw and yv axis. In case left-handed view reference system, a reflection of the one of the viewing axis is also necessary. So here, original position, then translation, then we need to rotate the object so that it can be aligned with the world coordinate. Aligning of viewing and world coordinate axis using a sequence of translate, rotate, transformation. First, do this translation, then translation to the origin, then we need to apply 3D rotation procedure so that those all axes can be aligned with the world coordinates. Okay, this is the viewing coordinates or the object coordinates which should be aligned with the world coordinates, so that we can map these things. Therefore, the composite transformation matrix is given by this. First translation, then the rotation which is done by sequentially Rx, Ry, Rz. There is another way to generate composite rotation matrix. A composite rotation matrix can be directly generated by calculating unit u, v and vectors. If we know the n and v vectors, the vectors are calculated as like this. So you can go through this context or text in the book also how we can do these things. It is a bit complex. I'll try to I'm not going to give too much importance on this point about how we can transform these things for viewing process, but I'll try to make you understand what is important, why we need to do this. Then we are going to understand what is projection. There are two basic ways of projecting objects into the view plan. It might be parallel projection, it might be perspective projections. In parallel projection, z coordinate is discarded and parallel line from its vertex of the objects are extended until they intersect the view plane. The point of intersection is the projection of the vertex. We connect the projected vertices by line segments which correspond to connections on the original objects. Let's see what it means. So parallel projection of an object to the view plane. Here this is the object, this is the view plane. So here is what it says. The parallel projection z coordinate is discarded. So we don't count the z coordinate here. The point of intersection is the projection of the vertex. Point of intersection is the projection of the vertex. We connect the projected vertices by line segments which corresponds to the connection to the on the original objects. So this is the viewing plan and this is the viewing direction, and which this connects these lines, dotted lines. In that point we will draw the objects, that is the projections of this object in this view plane. So that is parallel, because we are not considering about the 3 dimension, we are considering only this face. So we are not considering the z direction. Perspective projection is a different projection, where in a perspective projection on the other hand produces realistic views but does not preserve relative proportions. In perspective projections, the lines of the projections are not parallel. Instead, they all converge at single point called the center of projections or projection reference points. The object positions are transformed to the view plane along these converse projection lines, and the projected view of an object is determined by calculating the intersection of the converse projection lines with the view plane. So here you can see what is perspective projection of an object to the view plane. So actually there should be a center projection, and what happens in case of perspective projection, we cannot keep the appropriate proportion of the original object, but in case of parallel projection we can keep that, because we discard the z coordinate and we will only take the parallel view. But here we are taking the perspective view from the center of projection which is crossing through the viewing plane, and that projection, that center of projection might be anywhere. That might be before the viewing plane, that might be after viewing plane, and it depends upon you. That is why this is center of projection, or you can say reference point. This is converging point to the center of projections, and this happens always. Those every line should be converge to the center of projection. It might intersect the viewing plane. So again, this is another example of parallel projections. Here you can see orthographic parallel projections. This is oblique parallel projections. So orthographic is perpendicular, or oblique is not perpendicular. Okay. Orthographic projection can display more than one face of an object. Such an orthographic projection is called axonometric orthographic projection. It uses projection planes that are not normal to a principal axis. They resemble the perspective projection in this way, but differ in that the foreshortening is uniform rather than being related to the distance from the center of projections. Parallelism of lines is preserved, but angles are not. Here you can see angles are not preserved. Angles are not preserved. But in case of general parallel projection, we try to keep it normal. The most commonly used axonometric orthographic projection is isometric projection. The isometric projection can be generated by aligning the view plane so that it intersects its coordinate axis in which the object is defined at the same distance from the origin. This is the isometric object. So this is the projector. This is a projection. This is a projection plane normal. This is a projection plane. So isometric projection of an object onto a viewing plane. What it says, isometric projection can be generated by aligning the view plane so that it intersects its coordinate axis in which the object is defined at the same distance from the origin. So distance should be same. The distance of this point should be same. Okay. Like that way we need to present the thing. So there is again another projection, that is oblique projection. An oblique projection is obtained by projecting the points along parallel lines that are not perpendicular to the projection plane, but there is angle. For a Cavalier projection, the directional projection makes a 45-degree angle. Like here, this is a Cavalier projection of the cube, 45 degree or 30 degree. Cabinet projection of the cube of the unit cube. There are different types of perspective projection also. It might be depending upon the perspective point. This is 2-point perspective projection. This is 1-point perspective points. Okay. So this is all about 3D viewing. You can go through the context in the book also, in this through this slide also. And if you find it difficult to understand, please let me know. I have gone through a bit first to cover this one, and so there might be some fault remains, or there might be some thing which you might not understand. Then let me know. And also, for more learning or for knowledge, please go through the books or any literature. If you have any doubt, please let me know. We'll try to resolve it over Google Meet. Thank you.